So hello everyone, this is Tanya. I'm one of the TAs assigned to the aircraft design course taught by Professor A.K. Ghosh. So we'll go over the contents of the previous assignment and we'll do a brief recap of the complete lecture series. Okay. So the first question that was asked here was, when the center of gravity of an aircraft moves rearward, then the effect on long period mode will be. I know you have not been taught short period mode and long period mode, but this question doesn't have to deal with any of that. So don't get confused by the long period, short period. It just is the effect on the stability. Okay. So when you move the center of gravity of an aircraft rearward, that is towards the neutral point, considering your aircraft was initially stable, then it will be less stable compared to the previous position of center of gravity. Okay. For this question, you don't require the information on long period or short period mode, but we will go over it in a while. Okay. Okay. So this will be less stable as compared to the last center of gravity position. Okay. So the next question is, when they've given you the dynamics, that is delta W dot. W is the velocity in Z direction. Okay. And Q is the pitch rate. So they've given you the dynamics in this form. And they've asked you to find out A and B, where they've given you the, what have they given? They've given you the undamped natural frequency, that is omega n, and damping ratio zeta. Let's just go over the derivation of the short period mode, long period mode. What are they? Just briefly. Okay. So before that, this has to deal with the dynamic stability. Okay. So for dynamic stability, what are the precursors we need before we get into the equations? I'll just go over them. So we have various kinds of forces acting on the aircraft. Okay. So you have aerodynamic, you have gravitational, and then you have propulsive. Aerodynamic are what? Lift, drag, basically those forces that depend on the oncoming velocity. So they depend on the oncoming velocity. Okay, gravitational is just the weight of the gravitational acceleration. And propulsive in our case is just thrust. Okay, then what we take into account are different reference frames. For this analysis, we will require two. One frame, which we assume to be fixed in space. Okay, so assume it to be the center of the earth. It's just some inertial reference frame that with respect to the aircraft, we can assume to be fixed in space. Okay. The body frame, which is attached to the aircraft, the axis that we have been dealing with throughout this course, that is the x-axis towards the nose of the aircraft, towards the oncoming velocity, y-axis towards the right wing, and z-axis vertically down. Okay, so this reference frame moves with the body. Okay, so now let's look into the equations of motion, where you have your Newton's equation of motion, F equal to mdv by dt, where v is the velocity vector of the aircraft. Okay, so it has three components, u, v, w. It's given here. So the two frames, let me represent them by I, j, k for the inertial reference frame. And small I, small j, small k, the body reference frame. Okay, so all of these quantities that we have, that is force, oncoming velocity, the omega, which is PQR in the body frame. You have the moment, you have the angular momentum. All of these terms we know we can measure in the body frame. Okay. In the previous lectures, when we dealt with static stability, all of them had dealt with these terms that are measured in the body frame. Okay. So, but our Newton's laws of motion or the Euler's equation, both of them are defined in an inertial frame. But we have our quantities in the body frame. So we need to convert the inertial equation in terms of the quantities that we have or we can measure. For that, what do? We employ the transport theorem. This is the transport theorem. What does it state? It states that, yes, so the differentiation, if you have a vector A, the differentiation of the vector with time in the inertial frame is equal to the differentiation of the vector in the body frame plus omega cross A. Okay, how did we come to this formula? You must have studied this in dynamics. Even if you're not familiar, I'll just briefly go over it. So let's take a vector A that is defined in both the frames. It's the same vector, but we'll define it in two different frames. So you have its three components, let's say AX capital I cap, this is in the inertial frame. Then you have AY J cap, and you have AZ K cap. Now the same vector will define it in the body frame with different components. So let's say AX I cap plus AY J cap plus AZ K cap. Now let's differentiate the vector in the inertial frame and body frame and see how we can relate the two. Okay. So if I were to do dA by dt in the inertial frame. Okay. So what do? We do dAx by dt I cap plus AX d I cap by dt plus dy by dt j cap plus ay d j cap. The ij cap, they are the unit vectors in the inertial frame. Okay. dt plus az daz by dt a cap plus az d a cap by dt. Okay. So now this dAx by dt, let's just leave it there. These terms, these three terms, we'll leave it as it is. What will happen to these three terms, the other three terms? Di cap by dt, what is it? What is di capital? Di cap by dt. What is this value?
No, maybe 0.
It is 0, exactly. It's 0 because the I cap, J cap, K cap are fixed with respect to time. Okay, so you're assuming it to be the inertial axis. So it is fixed with respect to time. So di cap, dj cap, dk cap, the capital ones with respect to time are 0. Okay, so all of these terms vanish. All of them go to 0. Okay, now let's repeat the same process in the body frame. So you differentiate in the body frame. So you have dA by dt body frame. What do you have? You have dAx by dt small I cap plus AX d I cap by dt plus dy by dt j cap plus ay dj cap by dt plus daz by dt k cap plus az d k cap by dt. Again, let's leave these quantities as such. Okay, let's just leave these quantities as such. What is this? What is AX or what is di small I cap, d small I cap by dt? This is not exactly d in the body frame. Okay, just keep that in mind. You're just differentiating each of those vectors. Okay, that's all. Yeah, so what is d small I cap by dt? What do you think it is? The body frame moves with the aircraft, right? So it is not stationary. This di cap by dt will not go to 0. What do you think the value will be? What is the rate of change of the x-axis of the body frame with respect to inertial frame or with respect to time? What is the rate of change? So you have, let's say you have a body axis x or I, and it is changing with respect to time. What is this quantity? Rate of change of I, rate of change of x-axis, rate of change of y-axis. What do you think it?
Angular rotation, it is happening.
Angular velocity, yes. So rate of change of I vector will be the x component of the angular velocity. right? So it will be, where is omega? So it's basically this, right? So when you have these three terms, it comes to omega cross A in the body frame, okay? A in the body frame. So these three terms constitute omega cross A. Now this is defined as the differentiation of the A vector in the body frame. This is dA by dt body frame. These three terms come as omega cross A. Again, A is in the body frame. And this term, this is dA by dt in the inertial frame. Okay. So now we can see how we have come to this transport theorem that relates the differentiation of a vector, any vector in the body frame to its inertial frame derivative. Okay. Now we employ this relation in our Newton's equation. Okay, so here our vector is VC. So in place of A, you plug in VC and you get the same equation. And your entire dynamic equation is now in the body frame, comfortable for you to work with because you're measuring all your quantities in the body frame. Similarly, this is translational dynamics. Now, similarly for rotational dynamics, we have the similar equation, okay, dH by dt, where H is angular momentum. How is it defined? This was basically F is dP by dt, where P was linear momentum. And okay, just a second. Okay, let me write that again. So your Newton's equation was F is dP by dt, where P is linear momentum mv. Here I'm denoting it by Vc. So, and then we do dP by dt. Since the mass, we're assuming it to be constant, we take it out of the differential. It is dVc by dt. Similarly, for rotational dynamics, you have m equal to dH by dt, where h is the angular momentum. How is h defined? P is mvc. How is h defined? Just take analogous terms. If you have mass for linear acceleration or linear motion, what is the analogous term in rotational motion?
Moment of inertia.
Yes. So you have a moment of inertia matrix J. And what about V? V is the translational velocity. Sorry, it's here. Okay, so what will be the analogous term in rotational case? The rotational velocity. Right? So angular velocity W or omega in this case. Right? So H is equal to J omega. Just similar to the previous case, plug those values in here and you have this equation which is in the body frame, where H is J omega. Okay, so here if you just have to substitute J omega in terms of in place of H. So I'll just like to point out again, all of these quantities, force, velocity, omega, the moment, angular momentum, everything is measured in the body frame. Okay, we have our sensors to measure those quantities in the body frame. Hence, we employ it here. We change our inertial dynamic equation into the body frame for ease of computation. Now, when you substitute these values into the equation, that is omega is PQR, V is UVW, and you substitute these values here, you have set of 6 equations, right? So you have Fx, Fy, Fz. This is a vector. Both of these are vectors, right? So you have 3 equations for force and 3 equations for moment in the 3 directions, that is Fx, Fy, Fz, and then you have Mx, My, Mz. Mx, My, Mz, the moments in the 3 directions are represented by Lmn, okay? That's given here. Okay. So when you plug in those values, you get your 6 equations of motion like this. This is a 3 in the for translation motion, and these are 3 for the rotational motion. You have in the 3 directions, you have Fx, Fy, Fz, and then you have Lmn. What are Lmn? This m vector that we saw here. Okay. Right. So now we can see that on the right hand side, you have the force decomposed into the three forces, primary forces that we had discussed. That is the aerodynamic force, the propulsive force, and the gravitational force. Now, aerodynamic and the propulsive force both are measured in the body frame, but gravitational force has to be resolved into the body frame. Okay. For that, we bring into picture Euler angles. Because gravitational force is acting vertically downwards, the aircraft might not always be oriented, the body frame might not be oriented in that direction, right? So we need a definition of a global orientation. For that, we bring into picture the Euler angles, psi, theta, phi. It is to be noted that you're not supposed to, this is not pitch, right? That's what I've written here, elevation, not pitch. And psi here is not yaw. Do not confuse it with yaw or pitch. I'll just tell you what these three angles are. Psi is an elementary rotation about the inertial z-axis. ZE or Z earth or Z inertial is what I've represented the inertial axis with. An elementary rotation about the Z inertial axis is represented by this psi. That is not yaw. What was yaw? How was the angle yaw defined?
Beta.
Beta is side slip, right? How is it different from yaw? Anyone? Okay, so yaw is just with respect to any frame of reference that you take. When you take off your aircraft, you have a ground reference frame. How much you yaw your aircraft or turn your aircraft with respect to that frame, right? You deploy your rudder and you turn your aircraft, you yaw your aircraft. That angle is yaw. It has nothing to do with the global orientation of your aircraft with respect to inertial frame, okay? Do not confuse it. Then you have theta. After you do an elementary rotation about the z-axis, you have a new xyz axis. So let's just draw that. You had initial xe, ye, z. Okay, so this was your inertial axis. Now you performed an elementary rotation about the z-axis by an angle psi. Yeah. So what happens? Your x and y axis move. So this is xi. Now this is your new x1, y1, and z remains the same. Now a rotation about this new y-axis is called this theta. It's not the pitch. It is a rotation about this y-axis. Okay. So when you rotate about the y-axis, y1 remains constant, but x1 and ze both change. Okay, so it can be something like z can come here. So this will be z2. You have an x2 here. And the third and final rotation is phi, that is about this x2 axis. Okay, so if you perform these three rotations, you will arrive at your body frame. Okay, so a rotation matrix that involves these three angles can easily convert any vector from inertial frame to body frame. Okay, so if you perform these three rotations in sequence, that is, you perform your psi about z, then you perform your theta about the new y-axis, and then you perform your phi about the new x-axis, then your inertial frame can be coincident with your body frame. Okay, so what this does is it represents the orientation of the aircraft with respect to inertial frame. That is the Euler angle formulation. Why do we do this? To convert your gravity, these forces, this Fgx, Fgy, Fgz, into the body frame. And that is given here in these forms. Okay. Also, another requirement of these Euler angles is to have its relation with PQR, the relation of its rates with PQR. PQR is angular rates. Okay. So it's not exactly, so P is not directly phi dot, Q is not directly theta dot, and R is not directly psi dot. Okay. So the relation is given here. These are the two areas where we employ the Euler angles. Now let's go into longitudinal dynamic stability. Now here we had, for each of those axes, we had X, Y, Z, and LMN for all three axes. Now if we take just the longitudinal dynamics, which axis and which forces or which moments will remain? You tell me. These are your 6 forces and 6 moments. if I just take motion in the longitudinal plane, what forces and what moments will remain? Can you tell me? What is the longitudinal plane of the aircraft?
The pitch.
XY plane.
XY plane is longitudinal?
XZ.
XZ, yes. So what forces and what moments will remain? Longitudinal is XZ plane. Motion in the XZ plane. What are the motions in the XZ plane? What forces do you have?
Lift and weight, and the motions are
Pitch and
pitch up, pitch down.
pitch up, pitch down.
Okay, so you have lift and drag. You can have it in the other axis as well, right?
And the lift on the wing and the tail.
Okay, so basically from these 6 forces or 6 forces and moments, you have Fx, Fy, Fz, sorry, Fz and M. M is pitch, right? So it corresponds to velocity u, velocity v and pitch rate. Correct? These are the only ones that are retained. The others are not relevant for the longitudinal dynamics. Okay. So these are the 3 equations that we have retained. That is, this is the one for u, that is u dot, v dot, u dot, w dot, and q dot. So these are your 3 dynamic equations that you've taken for longitudinal dynamic stability. Okay. So it's the same equation. I've just written it in a different form here. Then what is done is, since these equations are highly nonlinear, you have products and sine theta and all of that highly nonlinear, it's difficult to analyze stability. So what do? We try to linearize it about equilibrium point. For an aircraft or longitudinal dynamics, longitudinal stability, what do you think is the equilibrium point? What is the equilibrium point?
Neutral point.
Yeah, neutral point. What is neutral point?
Our aerodynamic center we'll have, no? Yeah.
Okay. What was
CG,
okay?
man, CG.
Okay, can all of you tell me what? Let's start with CG is where the forces act. Fine. Where the gravity force acts. What is aerodynamic center? How did we define aerodynamic center?
About which change in angle of attack doesn't change the movement about it. There is a constant movement.
Yes. What is neutral point?
The point at which, if the center of gravity lies, the aircraft becomes neutrally stable.
It is
Okay,
same
but
as aerodynamic center, but it is just for whole aircraft.
correct. Both of you are
Yeah.
right. It's the same thing. But when you analyze dynamics, when I say equilibrium point, equilibrium state of an aircraft, it does not refer to these points, right? It means some condition at which the aircraft is flying, which we consider to be equilibrium. We had discussed this multiple times in the previous.
Okay, ma'am, then it will be lift equal to weight and thrust equal to drag.
Cruise, correct. Lift
Okay.
equal to weight, thrust equal to drag. That is one of your equilibrium points. So we had discussed this when we discussed static stability, where I said that if you give it some disturbance, it deviates from the equilibrium point and tends to come back to the equilibrium point. Okay. Do not confuse it with the aerodynamic center or neutral point. Okay. Equilibrium point is a point at which you want the aircraft to function, right? In our case, where all the sum of the forces, sum of the moments are 0. So that is lift equal to drag, thrust equal to weight. Thrust equal to drag, lift equal to weight. Okay. Cruise condition. So to linearize these 3 equations, we take one equilibrium condition represented by U1, V1, W1, which is at cruise. And then you apply a small perturbation to it. So perturb at the equilibrium, right? It's called the small perturbation theory. You can look it up in any of those aircraft stability books. So our equilibrium point is this. U1, V1, W1. That is equilibrium point. So now we linearize about this point. Okay. So all of those quantities will have that. So you will have fx1 plus some small fx. You will have fy1 plus small fy. You will have fz1 plus small fz. All of those terms, okay, even moments, you have q. So q1 plus small q. What are the other terms here? We have p1 plus small p. All of those terms, you have subscript 1 denotes equilibrium and the small letter denotes its perturbation, small perturbation. Now, when you perform several simplifications and you change one simplification that we take is stability axis is chosen along the velocity direction, you have simplified equations of this form for longitudinal dynamic stability. So 3 equations. These 3 equations are simplified into this form. Okay. Again, your dynamic states are U, W, and Q. Now, when we perform all the simplifications, finally, we get 3 equations in U, W, and Q as this. Okay. So now you can see all these derivatives here. That is all these coefficients here. That is XU, X alpha, X delta E, ZU. These are stability derivatives. And these are just derivatives of those forces with respect to U, with respect to alpha, and with respect to Q. Okay. What comes inside that, they have several of those aerodynamic parameters. So your XU, X alpha, X delta E, ZU, Z alpha, ZQ, Z alpha dot. What is alpha dot and why does that come into picture? Q is the pitch rate. What is alpha dot? What is alpha dot? What is alpha?
Angle of attack.
Yes. And so alpha dot is rate of change of angle.
Rate of change of angle.
Yes. So why do you think that comes into play? If you're pitching your aircraft, you have the pitch rate. Okay. Theta is the pitch and Q is the pitch rate. Why do you have alpha dot? And how is it different from pitch rate? Because both of them are in the same axis, correct? So how is it different from pitch rate? What is alpha dot? Why does it come? Why is it different from pitch rate? Anything? Yes. I didn't hear you.
Wings can be at different angles. It can be always at the pitching axis of the.
Okay. Okay. Yes, fine. Okay. Anything else?
If you consider an aircraft doing a loop, the aircraft might the pitch rate might be completely different from the angle of attack.
Yes, yes, correct. Another thing is your pitch rate is something that you give, right? So Q you can give, but alpha dot is how the aircraft will behave. So if you require it to fly at some alpha, you give a particular pitch to it, but it takes some time to reach that alpha. So the alpha is varying, right? So that's another one reason. So all of these reasons are valid. Okay, so that's how Q is different from alpha dot. Okay, so now let's get back to our coefficients. Z alpha dot, Z, okay, delta E, these terms, we just keep it different. So you have MU, M alpha, this should be M alpha, MQ, M alpha dot. All of these terms are a function of your aerodynamic parameters, aerodynamic coefficients, like CL, CD, and their derivatives. So we had some derivatives like CL alpha, all of those terms, right? So all these coefficients are some functions of your aerodynamic parameters and their derivatives. While these 3, that is X delta E, Z delta E, and M delta E, are derivatives with respect to your control parameters or control derivatives, okay? So you have terms like CM delta E, such terms. With deflection and elevator, how do these terms change? We also had CL delta E, right? So these 3 circled quantities are a function of your control derivatives, whereas the other parameters, other coefficients are functions of your aerodynamic parameters, aerodynamic derivatives. Okay. So now we can represent this equation. Let's get to this Laplace transform in a little while. Before that, you can represent u dot in the matrix form, in a simplified form. Q dot. Now Q is theta dot. Okay. And similarly, you have a relation between omega W and alpha. Okay. So here you can have an equation of this form. You have delta U, delta W, delta Q. Okay. Here, all of these coefficients come into play. You can just delta U, delta W, delta Q, what I wrote is the perturbation. But in the previous slide, we had seen that the perturbations we are representing just by the small letters, not by delta. Okay. So you just have this relation where, well, let me just write for the first. W in is basically alpha by, I think, horizontal component of velocity. It's related. Okay. So you have some x alpha term here. There'll be one U component. And in terms of Q, it is 0. Then you have for the other three cases. Okay. So you have something x dot equals ax, something of this form. This is the equation that we get for the longitudinal dynamic analysis. Now we apply a Laplace transform on this to obtain an equation of this form. Okay. If you are to open up this equation, if you are to open up as in multiply the matrix and write it down, you will get an equation, a characteristic equation, we're taking the determinant of this form, right? You get a fourth order equation. Now, you can ignore this for now. It's basically just something to deal with stability. For the equation to be stable, we employ Routh criteria. For that, all of these coefficients must be greater than 0. You have these three conditions. You don't need this for this analysis, so I'll just skip that. But you can obviously go through some notes and see that. Routh criteria just says different conditions that tell you how the system will be stable. Okay. Now, when we have this fourth order equation, we have 4 roots. Now, for this aircraft case, what we see is that these 4 roots come in the pair of 2 complex conjugates. What do we mean by complex conjugates? The 4 roots are, let's say, A plus or minus IB, C plus or minus ID. Okay. So if your roots of the equation are in the form of complex conjugates, how do you think the behavior will be? If I were to take with time and your state, let's just say X or S, whatever, how do you think the behavior will be if you have complex conjugate roots? You haven't been taught this, I know, but just think about it. Okay, so its response will be of the form of an oscillatory form. Okay, so if it is stable, it will oscillate and come back to equilibrium. If it is unstable, just draw another case, it will diverge. Okay, it will not come back to your equilibrium point. This is for dynamically stable case. This is for unstable. Okay, so how do we define stability? By this criteria. So one of the main criteria is that this quantity, that is the real part of your complex conjugate roots, should be negative. That is A comma C must be less than 0 for it to be stable. Okay. Now in these 2 roots, if your magnitude of A is larger, if magnitude of A is larger than magnitude of C, both the roots are stable. If magnitude of A is larger than the magnitude of C, which one will decompose fast? So let's just take 2 cases. Okay, so this is case 1, this is case 2. Which curve 1, curve 2? Which curve do you think will correspond to this root, this pair of roots? This one. If magnitude of A is larger, which curve do you think corresponds to this root? So its solution is of the form e raised to at, right? When you solve the differential equation, you get the solution of the form e raised to at, which is why you have the oscillatory nature. So if you have a larger magnitude of A, it will decompose faster, right? It will reach the equilibrium faster. So that is referred to as short period mode. Now, if your magnitude of C is less, so it will take a longer time to reach the equilibrium. So that is referred to as long period mode. Okay. Short period mode has a high magnitude root, so it converges faster to equilibrium, right? So it has a higher convergence rate. Long period mode has smaller roots, so it takes a long time to converge to equilibrium. Okay. So these are your two roots, short period and long period. Now let's see their approximations and how we can compute the various properties. Before that, let's just a brief introduction or brief review of a second order system. Let's just take a forced spring mass damper system. Okay. So this is m x double dot plus c x dot plus kx equals f of t. This is t. Okay. So this is the equation for a forced spring mass system. You take its characteristic equation, you get roots of this form, right? And where this omega n is root of k by m. Omega n is the natural frequency and zeta is the damping ratio. Okay. So this you would have studied in any dynamic course or any vibration analysis course. Okay. If I substitute these values back into this equation, you get an equation of typical second order equation. Okay. This will be useful in the analysis ahead, which is why I just went over this. Depending on the nature of these roots, what is inside the square root, you can get either complex roots or positive roots, negative roots, anything. Okay, so if it's a complex root, that is if your km is greater than c by 2m square, you have oscillatory behavior, right? So let me just see that. You can either have oscillatory behavior, or you can have undamped behavior, or you can have critically damped behavior. Okay, so these are the three cases that correspond to this damping ratio. If damping ratio is 1, it's critically damped. If it's greater than 1, it's the undamped case, and vice versa. Okay, so now let's go to the two approximations. So our main equation, this was our main equation that we obtained after the Laplace transform. For the short period mode approximation, we assume u to be 0. So what do? We eliminate these two rows, right? So we eliminate these two rows. What is your remaining equation? Remaining equation is of this form. It's a 2 cross 2 matrix. Okay. And then, so you have a second order system. Substituted, you find equations of this form where omega n and damping ratio. You don't need all this. I'm just briefly going over it. Similarly, for the phugoid mode or long period mode approximation, you take alpha to be 0. So for that, what do? You ignore these two rows, this row and this column. And again, you have a second order system. Okay. Now let's go back to our question. Where is the question? Yes. So short period mode approximation, where we have this 2 cross 2 matrix. So we find the roots of this equation, or we find the characteristic equation of this motion and equate it to a typical second order system to find the coefficients. It's as simple as that. Okay. So let's just go over it. If I find the characteristic equation, so that let's just take this is x dot equals ax. So how do you find the characteristic equation? A minus lambda I equals 0. You tell me the values. What is a minus lambda I? What is the first term? What is the first term? If this matrix is A minus lambda I, let me just write it down. Minus 1, 1, A, B. This is A minus lambda into I. I is an identity matrix, so it's just 0, 0, lambda. Okay, now tell me. So it's just minus 1 minus lambda, or 1 A, B minus lambda. It's determinant. Just tell me what it is. What will be the final value or the final equation? Minus b plus lambda minus b lambda plus lambda square minus a equals 0. So rearrange it as lambda square plus 1 minus b lambda minus a plus b equals 0. Now what was your second order equation? It was lambda square plus 2 eta omega n lambda minus plus omega n square, correct? Was this the equation? Equate these terms and try to find out. So it's like 1 minus b is 2 eta omega n. Omega n is 5, eta is 0, so this is 0. So b is 1. This is first answer, b is 1. Plug it here, so you'll have minus a minus b equals omega n square, which is 25, minus a minus 1 equals 25, a equals 26. Okay, so this is the right answer, equals minus 26. That's the right answer. Okay, now let's go to the next series of questions. The necessary condition for a stable aircraft is, we have dealt with this multiple times. So what is the necessary condition?
4th.
Yes, Cm alpha less than 0. Which condition holds true to trim the stable aircraft at positive angle of attack? So stable aircraft.
Cm naught is greater than 0 and Cm alpha should be less than 0.
Correct. For stable aircraft, we can neglect these two options because these two are unstable aircraft. So these two are cancelled right away. If you have to trim the aircraft at a positive angle of attack, your Cm naught has to be greater than 0. So this is the right answer. Why? Because this is your Cm naught, Cm versus alpha graph. So this is your Cm naught and this is your trim point. This is a positive angle of attack. If your Cm naught is equal to 0, this is your trim location and your trim angle of attack is 0. And if your Cm versus alpha graph is like this and Cm naught is negative, so this will be your Cm naught. This will be your trim location. Your trim angle of attack is negative. So they've asked for a positive trimming angle of attack. So this is the,
Ma'am,
yes.
now for negative Cm naught at
Yes.
trim at 0 alpha, we will have a negatively cambered aerofoil.
No, so Cm, okay. So
For the
this is
third line that you have drawn.
Cm naught negative. So for Cm
Yes.
naught negative, you have the Cm alpha, Cm at what is this? Cm AC of the wing will be negative, correct?
Yes.
If Cm AC of the wing is negative, then your airfoil is positively cambered. Yes.
Ma'am, for alpha equal to 0, if Cm naught, we are having a negative value of Cm naught for alpha equal to 0. The third line that you have drawn.
Yes. Yes.
Which type of cambered aerofoil it will have?
See, that is the one I'm saying. So that this means Cm naught is negative, right? This entire
Yes.
term means Cm naught is negative. Cm is negative. It's a wing only configuration. So you have just a wing. So let's just take this.
Okay.
This is your center of pressure. This is your aerodynamic center. Now this is a positively cambered airfoil, which is why your center of pressure is behind aerodynamic center. So when I transfer the forces, lift and drag, I get a negative moment here. This is your Cm naught. Correct?
Yes, ma'am. Got
So
it.
for a positively cambered airfoil, you will have a negative Cm naught, which is why we need to make adjustments in the tail. In the tail setting angle, there was some contribution of the tail towards Cm naught, right? So you can set your tail at different angles to change your Cm naught value. If it is a wing only configuration and your airfoil is positively cambered, your Cm naught will be negative. Okay. Another thing that you can do is that you can have a reflex airfoil. So reflex airfoil, your Cp will be shifted at least towards the aerodynamic center. So your Cm naught will at least be 0. But that's not the case. Actually, Cp for a reflex airfoil, reflex is this. Right? So you have a slight upward curvature towards your tail, which ensures that your Cp is at least slightly ahead of AC. This means that when you transfer the forces, you get a positive moment. Positive Cm naught at AC. You have a positive Cm naught. So 2 ways to ensure that you have positive Cm naught is reflex airfoil and the tail setting angle. Okay.
Understood, bro. Thank you.
Next question. Same stable aircraft at 0 angle of attack. We discussed the 3 graphs.
Fourth
Cm
option.
should be 0. Yes, Cm naught should be 0. Okay. Next question. Okay. I think we have done something similar. The fixed wing UAV, the tail area is 1/4 of the wing area, and wing and tail are rectangular in shape. In addition, the following data is applicable. Weight of the aircraft, they have given you cruise velocity, CL alpha of the tail, alpha L equal to 0, the mean aerodynamic chord, span, Cm naught, tail efficiency factor, XAC of the tail. You have control surface effectiveness parameter, d epsilon by d alpha and epsilon naught. Okay, let's look at the questions. Okay, the location of neutral point in meters for the above fixed wing from the leading edge of the wing. How do we derive the neutral point? We have done this. We begin with the moment at the leading edge, moment at the CG. We do this calculation. Do you remember the derivation? We'll just go over it for a simple configuration. Okay? I'll just take a wing and tail and we'll try deriving it. We did this for a 2-wing canard and tail configuration. So this should be fairly simple. Let's just take fuselage reference line. This is your wing. This is your tail. This is CG. This is NP. This is the aerodynamic center of the wing. This is the aerodynamic center of the tail. Take your reference point to be the leading edge. This is XAC wing. This is XCG. This is XNP. This is XAC tail. Okay, so let's start with moment at the CG. What contributors are there towards the moment at the CG? You have lift, drag, you have lift, drag. Just tell me, what are the contributors? How do we begin this derivation? We start with the lift. Take lift of the wing.
Lift of the wing multiplied upon XCG minus XAC of wing.
Yes. Okay.
Then minus of the lift from tail multiplied by XACT minus XCG.
CP minus XCG, yes. Anything else?
We can ignore drag components, but
Yes, we can
there
ignore
are-
drag. Anything else?
Movements about the AC of the wing and tail.
So you have, for tail, it is a symmetric airfoil, so you can assume.
It's 0, but there will be movement of wings around AC.
Yes, so you have MAC wing. And actually you should have MAC tail, but since it is symmetric, we take this to be 0. Okay, Now let's divide throughout by half rho v square SC bar to get it in non-dimensional terms. So what you get is CMCG will represent by CM. This will be CL into X bar CG is nothing but XCG by C bar. X bar AC wing minus CL of tail. X bar AC tail minus X bar CG. You have CM AC wing. Okay. Now CL is CL naught plus CL alpha. You get a CL naught into. Okay, here you have some other terms. You have this. You have area of the tail upon area of the wing. Then you have alpha tail here. Let me just rewrite this whole thing. This CMAC wing, you have minus S tail upon S. And you have a tail efficiency factor because the velocity seen at the tail is different from the velocity seen at the wing due to the downwash. Okay. You have a tail efficiency factor here. What is tail efficiency factor? Eta T is, what is that ratio? Velocity at tail,
Velocity at tail to velocity
at wing. Okay, so this is the tail efficiency factor. Then you have CL alpha tail into alpha tail, and then you have XAC tail minus XCG. Now, what is alpha tail? In terms of tail setting angle, the alpha at the wing, all of those terms, what is alpha tail? Alpha wing plus tail setting angle. And there's a downwash component that you have to subtract, epsilon. Okay, and epsilon is linearized. That is, so you have epsilon as epsilon naught plus dou epsilon by dou alpha into alpha. Right? So I plug that in here and substitute it into this term. Let's see what we get. Okay. Let me just write this equation again quickly. So you have CM is CL naught. Was it? CM is CL naught into X bar CG and X bar AC wing plus CL alpha into X bar CG minus X bar AC wing . Into alpha wing. Let me write that down because it's getting too long. Minus SP upon S, theta tail, CL alpha tail into 1 minus dou epsilon by dou alpha into alpha wing minus X bar AC. What else? What else are we missing? Wing. Anything else? Anything else? Okay, I don't think we're missing anything. Just let me know if I'm doing any mistake. I still feel we're missing a few terms. What are we missing? There are some terms missing. What are we missing? Can someone point it out?
Don't know, ma'am. I think it is all right. Maybe.
Okay, so let's proceed. I feel we're missing a few terms, but okay, let's proceed. Now we write Cm is Cm naught plus Cm alpha. How do we define neutral point? How do we define neutral point?
About which Cm alpha is 0.
Yes, okay. So if xcg equals xnp, Cm alpha equals 0. Let's plug in these conditions here. Cm alpha are those terms that depend on alpha. Okay, so Cm alpha is Cl alpha into x bar Cg minus x bar AC wing minus St upon S theta tail Cl alpha tail 1 minus dou epsilon by dou alpha into x bar AC tail minus x bar Cg. So now we plug in that xcg equals xnp. So this equals 0. This will be Cl alpha x bar np minus x bar AC wing minus St upon S theta tail Cl alpha tail 1 minus dou epsilon by dou alpha x bar AC tail minus x bar np equals 0. Now when we simplify this, that is x bar np will be equal to Cl alpha into x bar ACW plus St upon S theta t Cl alpha tail 1 minus dou epsilon by dou alpha x bar AC tail by denominator will be Cl alpha plus St upon S theta tail Cl alpha tail 1 minus dou epsilon by dou alpha. Okay, so this is your equation for neutral point. Now this derivation can be done every time, but I'll tell you a simple way to remember it. It's like a weighted average. Okay, so what it does is, so your weighted average or centroid or moment of center of mass that we had done in the previous lectures, it's something like that. It's like a weighted average. So x bar np is nothing but some weight into x bar AC plus another weight into x bar AC of the tail by W1 plus W2. Now, what are these W1, W2? For wing, it is nothing but Cl alpha of the wing. For tail, it is the effective Cl alpha, okay, with respect to, that's dCl by d alpha wing of the tail. Okay, so this entire thing is like Cl alpha of the tail, okay, when you differentiate it with respect to alpha of the wing. So those are your two weights. It's like a weighted average. Now, if you have you have another control surface there other than the tail, you have a canard ahead of your wing, you just add that. So what will happen? You will have one W3. You will have W3 XAC of the canard. We had done this derivation also, I remember, in one of the previous sessions. So it's just a weighted average of all these terms where the weights are the Cl alphas, are their respective Cl alphas or effective Cl alphas. When canard comes into play, there is no downwash. Okay, so this term will not be there. It will just be Cl alpha of the canard. Okay, so it's like a weighted average. Now let's try to solve this question. So this is your final equation. Write it down. So x bar np is Cl alpha of the wing in Denominator is basically the complete lift. Okay, so that's basically CL alpha of the entire aircraft. Okay, so let's compute this. CL alpha of the wing in the question is, you can actually just plug in these values and solve these questions now by yourself. You can, right? Just wanted to go over a few concepts from previous lectures. So you can just plug in these values. These are given to you in the question and you can find out. Okay, so ST upon S, they have told you that the tail area is 1/4 of the wing area. This will be 1/4. All the other parameters are given to you in the question. You can solve it, right? So this derivation is fairly simple, but you can try to remember this weighted averaging technique and you can solve it, okay? Next question, they've asked you the total lift curve slope of the UAV in per radian. Total lift curve slope is this denominator. What is that? CL alpha is CL alpha of the wing plus ST upon S beta tail CL alpha of the tail 1 minus dou epsilon by dou alpha, right? This is the total lift curve slope of the aircraft. Again, you have all of those values, plug it in and you'll get the total lift curve slope. Then what is the static margin of the UAV? How do you find this?
XCG minus XC.
We don't have CG, right? Is the CG given in the question? No.
Ma'am, in this static margin, we will take the ratio of this CM alpha and CL alpha.
So it's minus CM alpha by CL alpha. But do we have CM alpha?
Ma'am, we have DCM by D alpha and DCL by D alpha. So from that, I think we'll do.
Where do we have DCM by D alpha?
And CM alpha, we need to calculate.
Okay, how do we calculate CM alpha? How do we calculate CM alpha? I'm not sure either. Can you? Is it given in the question? No.
No, ma'am, it's not given in the question, but the place where I took the reference for this question, they have given the value of CM alpha in the question itself.
Okay. Okay. So I think this variation should be given to you. I think that data is missing. How did you solve the assignment?
I wasn't able to solve this question, and that's why I was asking 2 weeks earlier.
Okay. Okay. So I think this variation CM naught plus. Okay. Let me look into this.
Also, ma'am, the solution they have uploaded on the site, ma'am, I am unable to get it. How they have done it?
Okay. So I think this relation should have been provided to you with the quantities where you have CM naught and CM alpha. Let me just look into it. I will, yes, CM naught is given for the entire thing. CM alpha should also have been given. Okay, so I'll just make a note of it. I'll let the concerned TA know. Okay. Apart from that, did you have a question in the previous 2 questions? The other 2, you had all the data, right? All the data was given?
Yes, ma'am, for those questions, everything was given.
Okay, CL alpha is there. Okay. So it's just CM alpha. Okay. I'll look into that. I'll let the concerned TA know. So if CM alpha is given, it's just directly you plug it in and you get the static margin. Okay. Okay. So does anyone remember what the correct answer was? Because we'll need it for the next question. Okay. Doesn't matter. Now, with the static margin obtained in question 3, what will be the location of center of gravity of the UAV in meters from the leading edge? Okay, so once the static margin is known, I will talk to the TA. Let's just continue this. Static margin is X bar NP minus X bar CG. Now, static margin you will get from the previous question. X bar NP you will get from the first question. You can find out X bar CG, right? Okay. Next is identify the tail horizontal volume ratio. That is VH. This, I think all quantities are given to you. What was VH formula? What was the tail volume, horizontal tail volume ratio formula?
STLT upon SC bar.
So do you have all these quantities? ST you have, this you have 1/4.
For length, we need to have the XCG.
Okay, so these three questions you would not have been able to do. Okay. I will look into that and I'll ask them to update the response. But otherwise, if CM alpha is given, it is straightforward, right?
Yes, ma'am.
Okay, I will look into that. Okay. Now let's just go over all of the concepts that we studied in throughout the course. Just a brief recap, and you can ask me if you have any questions or anything else. These are the formulae, basic formulae that you need to remember. CL and it's a linear approximation. CL naught is CL alpha upon into alpha. So you have the graph, the symmetric airfoil, CL versus alpha. You have this graph. For a positively cambered airfoil, how will the graph be? Will it shift to the right or the left? Positively cambered.
Up, ma'am.
Left. It will shift left.
Yes.
Yeah,
It will
left.
shift something like this. So CL naught will be positive. Okay. Another thing that I need you to remember is this for the CM. Right. So let me do. This is CM versus alpha. This is CM versus CL. Okay. CM versus alpha. CM versus CL. This CM naught and this CM naught need not be the same at all for all cases. If it's a symmetric airfoil, it will be the same. But if it's not symmetric, the two intercepts will be different. So if they don't explicitly mention which CM naught they're referring to, if they just say CM naught, it is the CM versus alpha CM naught. So this is CM naught. This is some other quantity, CM naught 2 or anything else you can refer. If they don't explicitly mention anything, you assume it to be the CM versus alpha graphs intersect. Okay. Okay. Let's move to the next equation. This is known as the drag polar. We had discussed this even in the last lecture. So this is the drag polar. It's a relationship between coefficient of drag and coefficient of lift. So the two quantities, do you remember what they were called? What is this?
Zero lift drag.
Sorry?
And zero lift drag.
Zero lift drag. It's also called parasite drag.
Parasitic
Right?
drag.
And what is this?
Induced drag. Lift induced drag.
Okay. So for an airfoil, what will the induced drag be?
0.
0. Can you tell me why?
Because the
Because
flow is
aspect
2D.
ratio is infinite, so K is 0.
Correct. So as K is 1 by pi EAR, aspect ratio of an airfoil is infinite. So this induced drag, this I and this is P, induced drag for an airfoil will be 0. Okay. So this is the thrust required formula. We take the equilibrium condition, which is lift equal to weight and thrust equal to drag, and derive this.
Ma'am, another way of understanding zero induced drag for airfoil is that there is no vortex formation.
Yes, because there's no interaction. Correct.
Wingtip vortices are not present.
Yes, that is true. Correct.
So we can-
Thanks for pointing that out. Okay. We have a relation for velocity just directly from the CL lift equation, lift equal to half rho v square SCL. Then you have a relationship for V stall, where instead of CL, you just plug in CL max. Then you have rate of climb. Rate of climb is given as, this is basically power available minus power required by W. You have this derivation and you come up with this formula. This formula was important in a few questions because they asked changing this wing loading, does it affect rate of climb? Changing CL, or like what parameters affect rate of climb? So these relationships will be important for that. Okay. So if they ask you on what it depends, if you increase the wing loading, will the rate of climb increase or decrease? Such questions, these relationships will be important. Okay. Next, we see the difference between minimum thrust required condition and minimum power required condition. Now they are reversed for your propeller engine and jet engine. So maximum range of the propeller engine is associated with minimum thrust. It's also for a jet engine, it is the maximum endurance, and vice versa for a minimum power condition. We had discussed this twice. Can you remember why this vice versa is happening for propeller and jet? What differences lead to this? Okay, we'll get to that. Just remember that the differences between the CLCD ratios and the CLCD values for minimum thrust and minimum power. The difference between the jet and the thrust we had seen in this slide, propeller and the jet, propeller and the jet. So the power and thrust graphs are given here. We had discussed this quite a few times. Do you remember this? Can someone just summarize this? Why is this relationship vice versa? You just maybe 1 or 2 lines, just summarize it from the graph and the points that are given here. For a propeller aircraft, the power remains constant with respect to air. For a jet engine, the thrust remains constant with respect to air. Okay. Okay, I will give you these slides. You try to summarize it on your own. We had discussed this a couple of times. Then we have relationships for the minimum drag and the minimum power condition and how they're related to each other, right? So for the minimum drag, minimum power, we had seen in the table what the CLCD values are. Plug that in, you find out the relationship between their velocities. This was also important in a question where they asked which is greater than the other or by what factor. So if the ratio is 1/√3, or their actual ratio is 1/3. So just the nomenclature of airfoils. Leading edge, trailing edge, the line joining the leading edge, trailing edge is the chord line, mean chord line. The camber line shows you how much the airfoil is cambered. Okay, so these are the parameters by which we define those NACA airfoils. NACA 4 series, 5 series, 6 series. Just go through that before your exam. What are the considerations you have when you pick your airfoil? You want your CL alpha to increase. So you want a greater slope, but you also want to delay your alpha stall. What is alpha stall?
And CL alpha increase, it means in negative terms, no? Its value will become more negative.
L alpha is positive, right?
Oh, CL it is, not CM. Okay.
CL, yes. CL alpha should be positive. CL alpha will be positive, but we want it to be its slope. We want it to be more, but at the same time, we want your alpha stall to be delayed as far as possible. This point is alpha stall. Why does alpha stall occur? What is alpha stall?
Because of flow separation, the lift reduces.
Yes, the lift generation reduces beyond that point. Till then, it's a linear regime. After the alpha stall, the lift generation reduces. Okay. So next thing that we want is we want to have our CL max as high as possible. We want to have a higher critical Mach number. What is a critical Mach number?
With some local
The Mach number at which
Yes.
The free stream Mach number at which first time the flow becomes
Correct.
sonic.
Correct. So anywhere on the airfoil, if it encounters Mach 1, the free stream Mach number at which this occurs is called critical Mach number. We want to have a higher critical Mach number because we want to delay the occurrence of shock waves or supersonic regime as far as possible. Okay. Then what was drag divergence Mach number?
The free stream Mach number beyond which drag increases 10-fold time.
Yes, correct.
Exponentially.
Yes, so we want to delay both of these phenomena. We want to have a higher drag divergence Mach number. That should be another condition here. Drag divergence should be high. Then CMAC should be positive. We just discussed this in one of the earlier questions. CMAC should be positive. Okay. Why do we want CMAC to be positive? To trim the aircraft at a positive angle of attack. That's the only requirement. Yes. It does not affect stability in any way. Okay. So they might ask you some tricky questions. Okay. The other geometric considerations for the aircraft that we have, nose radius, thickness to chord ratio, the camber, all of these considerations take importance when you pick your NACA series. Okay. Then, yeah, this is critical Mach number, the free stream Mach number at which at some point on your airfoil you have Mach 1, beyond which there is a shock wave generated and your lift generation capabilities are largely reduced because there is a wake. Lift generation capabilities are reduced. Okay, so you want to delay this occurrence as far as possible, as late as you can. Okay, so now it's just a brief overview of the different airfoils. You have low camber, deep camber, all of those. What was this airfoil? This one?
Reflex camber.
Reflex. And what we just discussed, one important property of this. What is it?
That the CMAC will be positive.
Yes, CMAC will be positive. You have symmetric airfoil. What is this one? What was this airfoil? It's slightly flattened at the top.
Laminar airfoil.
It is called the supercritical airfoil, right? It was called the supercritical airfoil. What is the one benefit it has over the other airfoils?
It's meant for delaying the drag divergence Mach number.
Yes, precisely, correct. Right, you can delay, you flatten the upper surface, so you delay the occurrence of a shock wave, and it delays the drag divergence Mach number, correct. Okay, so the advantages of a supercritical airfoil are higher drag divergence Mach number, shock wave forms aft as compared to a typical conventional airfoil. Your shock wave is formed later, so your flow separation occurs later. That means there is reduced boundary layer interaction, boundary layer and shock interaction. Okay, so there is less drag. So these are the benefits of the supercritical airfoil. For reflex airfoil, your CMAC will be positive. That is the benefit. This was the vortex generation. What do winglets do? Okay, in the absence of winglets, the flow below the wing and the flow above the wing interact and generate huge vortices, which will have a huge impact on your lift generation. But if you have winglets, these tips, the vortices are reduced, right? So initially you had large vortices, but now when you've introduced the wing tips or winglets, these vortices are still present where the flow below and the above meet. They are still present, but their magnitude or their intensity is very much reduced. Okay, so their downwash problems, all of them are incredibly reduced, the induced drag and all of those. Okay, so that is the benefit of winglets. I put the slide because I think they've asked this a couple of times about benefit of winglet. What do winglets do? Something like that. Okay, so this is the movement of center of pressure with the change in angle of attack. The pressure at the top of the airfoil, represented in blue, is negative. The one in red is positive. Okay, so the net at which the forces act is the center of pressure. With the change in angle of attack, it moves. So it's somewhere, it peaks at somewhere here. So this is somewhere the center of pressure. When you reduce angle of attack, it moves aft. When you increase the angle of attack, it moves ahead. Okay, this is why we don't pick center of pressure as the point of doing our analysis, even though that is where the forces act. We don't use a center of pressure because throughout the flight regime, when the angle of attack changes, the center of pressure will also change. So it becomes very inconvenient for us to do our analysis, which is why we came up with aerodynamic center. It is the point at which these forces, moments don't change, or CM alpha is 0. That is changing pitching moment with change in angle of attack is 0, right? So it's constant. So you have an ease of analysis. Okay, this is just another.
Ma'am,
Yes.
are the winglets and wingtips the same thing? They
Yeah.
have a different.
Wing tips and winglets are the same thing. They are the same thing. Okay. This is just another representation of how the center of pressure changes when you change angle of attack. Okay. Now, if it's a wing only configuration, your CG has to be ahead of AC. So you're flying just a wing, the CG has to be ahead of AC for a stable aircraft. Now, if you introduce a tail, what do you think will if you introduce a tail, first and foremost, the point of consideration will be neutral point. Okay. the aerodynamic center of a wing is analogous to neutral point of an aircraft. So I introduce a tail. So now your neutral point location is here, right? So for a wing tail configuration, your CG has to be ahead of neutral point. Now, if I introduce a canard, right? If I introduce a canard, your neutral point location still has to be, so your neutral point location moves towards the canard. Why? Because a lift generating component is added ahead. In the previous case, it was behind because a lift generating component, the tail, was added behind. Okay. So in either case, what you need to remember is that neutral point has to be behind the CG. CG has to be ahead of the neutral point, both the cases. Okay. Yeah. Then for aerodynamic center calculation, these were the formulae. Don't think they will ask you any complicated such questions, but it's good to just remember the formulae. So aspect ratio was the ratio of the tip chord by root chord. Mean aerodynamic chord, you had this relation. And if you have like a combined surface, so if you had something like this, right, you didn't have a continuous surface, what you do is you divide it into two surfaces. This is surface 1, this is surface 2, and you find out each of these quantities, that is lambda 1, C1 bar, aspect ratio 1, lambda 2, C2 bar, aspect ratio 2, and then find out its overall C bar. How do we do that? How do we do this?
We can take average CR plus
Yes.
CT
We
divided
take
by
the weighted average.
We take the weighted average. It's, remember this, it's not just C1 bar plus C2 bar by 2, it's the weighted average. It is S1 C1 bar plus S2 C2 bar by S1 plus S2. Similarly, we do this for the other properties, any of the other properties. For example, AR, the overall aspect ratio of the wing is S1 AR1 plus S2 AR2 by S1 plus S2. Okay, weighted averaging. Then we'll just go over the static stability concepts. We've discussed this many times. This is the most important thing. Cm alpha has to be less than 0. Cm naught is only to trim the aircraft at positive angle of attack. Just derived these two things. Okay, so this was the term that was missing in that equation. Do you remember that? Yes, here you needed to thing plus epsilon naught or minus epsilon naught. X bar AC tail minus X bar CG. This was there. Okay. Yes.
But ma'am, we weren't given IW and
No,
wing
I'm just
setting
talking
angle.
about the
We don't.
derivation. No, just the derivation. That
Okay.
still is missing information. That is still true.
Okay.
Okay, I will check with the guide, with the other TA. Okay. So this is the Cm naught contribution of the wing. And this is the Cm naught contribution of the tail. This is the Cm alpha contribution of the wing. And this is the Cm alpha contribution of the tail. You have other surfaces, it will just be added just like this. How to ensure Cm naught greater than 0? We had seen one is reflex airfoil. The other one is?
Tail setting angle of attack negative.
Yes. So this ensure this term is positive. Okay. These are the two methods. Then we saw neutral location. It is analogous to aerodynamic center. CG location at which Cm alpha is 0. We even did the derivation, so it should be simple. Static margin is defined as minus dCm upon dCl. It's also the difference between the neutral point and the CG. Another question where we had seen, they had given you static margin and some fuselage contribution. So what do you do? So static margin is minus dCm by dCl of wing minus dCm by dCl of tail minus dCm by DCL of fuselage. Okay, just so on and so forth. Just keep adding it, and then you will get the final equation. This was one question that I remember. Okay. For directional stability and control, the conventions was right wing back is considered positive yaw. Okay, so if this is your fuselage and this is your wing, this direction, that is, this is considered positive yawing. Okay, so your fuselage changes like this. This is positive yaw. Then if your oncoming velocity is in this direction, this is considered positive beta. Okay, then a rudder deflection to the left generates a force. This rudder deflection towards the left is considered positive. This is positive delta R. These are the conventions. We had seen all the derivatives and what signs they should take in the previous week 11 series. So C and beta should be positive. In the previous case, Cm alpha should be negative. Here, C and beta should be positive. These are just the equations that come up when we deflect the rudder. Or what contributes towards stability, directional stability, vertical tail, and swept wing. Okay, these are the two contributors towards directional stability. Okay, for lateral stability, the conventions are right wing down is considered positive roll. So roll axis is the x-axis. Rolling towards the right is considered positive. How do we roll towards the right? You lift your right aileron up, deflect your left aileron down. It's considered positive rolling mode. Okay. For static lateral stability, you require CL beta to be less than 0. This is the condition for this case. And what are the contributors towards lateral stability? Vertical tail, high wing, or low wing with dihedral. These three contribute towards lateral stability. Okay. These are some equations that we repeatedly used in the questions. You need to remember this. And in the previous class, okay, let's just go one by one. This is epsilon naught plus d epsilon by d alpha. So each of those terms are mentioned here. I repeat again that this should be, this CL naught doesn't matter. This is entirely a dimensionless parameter. To ensure that this entire thing is dimensionless, CL alpha of the wing must be in per radians. Similarly, here CL alpha 2D must be in per radians. Otherwise, these formulas are not valid. Now, we had seen in the previous class that CL naught 3D also has a similar empirical relationship. CL naught 2D by 1 plus CL naught 2D by pi EAR. Okay. VH we just saw. This is the relationship. Okay. Then to trim, the angle required to trim the aircraft at given CL trim. This is your formula. So as your CG moves towards neutral point, this slope keeps reducing. So this is delta E naught plus d delta E upon dCL CL trim. This is also at trim. Okay. As your CG moves towards the neutral point, this slope keeps reducing. So CG is moving towards neutral point in this direction. And when CG equals neutral point, your slope is 0. Okay. So this is the relationship between the how much elevator deflection is required to trim the aircraft. Okay. This is the difference between yaw angle and side slip. So you take a reference azimuth. How much your aircraft is oriented away from that is called the yaw angle. But side slip angle is how much the relative airflow, what angle that is introducing into your, with respect to the fuselage reference line. This is your fuselage reference line, and this is your relative airflow. This is beta, okay? And towards the right, it's considered positive beta. Okay. Okay. We have come to an end of our session. Is there any questions that you have?
Yes, ma'am. The second question from assignment 12, ma'am. Ma'am, should we expect these type of questions in exam as well?
I don't think so. I don't think you will have such questions. That should.
Because ma'am, in the YouTube lectures, they haven't taught us this.
Yeah, so
Also,
it-
the prerequisites are performance and stability control, not flight dynamics part.
yes, no, dynamic stability has not been taught, so I don't think it'll be asked. This should not have been asked even here. So I don't think it'll be asked, don't worry.
Okay, ma'am.
Anything else? Any other questions?
Yes, ma'am. Just upload this video on YouTube on priority basis so that we can see it again.
Yeah, sure. I will upload it. The slides I'll upload it right now, right after this lecture. The video also by tonight I'll do it.
Yes, thank you, ma'am.
Anything else? Any other questions? So any doubts you have before the exam, put it up on the forum. We will try to respond as early as possible. The ambiguity in the week 12 assignment, I will resolve. I will speak to the other TA. But we can end the session here. I hope you all learned something from this entire course. Good luck with your
Yes, ma'am.
Yes, ma'am.
Thank you
Thank
very much.
Thank you.
Thank you very much.
Yes,
It was very useful.
Thank you.